Hello, and welcome to Lab 5. Choose your own adventure. In this lab, we will simulate the motion of a bouncing tennis ball using V-idle, and we will determine the contact force exerted by the ground on the ball in that motion. So, as we determined, the contact force was calculated to be 8.322 newtons, and we did determine a computation model to accurately match the observed data we got from Tracker. So in our lab, we used the momentum principle in relation to the motion of the tennis ball. We use Newton's second law of velocity, where final velocity is equal to initial velocity plus F net over mass times delta t to predict and update our position and velocity in a computational model with V idle. In this case, F net is not equal to zero, as we know, because of the forces acting on the object, and thus that velocity is, as we know, it's not constant. So in this case, during the fall of the tennis ball, we know that the force of weight acts on the ball and the force of drag. The force of weight in this case would be m times g, which is gravity, times negative g hat. In the case of the drag force, we know that to be the coefficient for drag, which is proportionate to the surface area of the object, times the magnitude of the velocity squared, times j hat. So in order to calculate contact force, we take this formula of F net represented as mass times acceleration. In this case, F net would be represented as force of gravity plus our force of contact. So we know the mass, so we solve by acceleration by taking the final minus the initial. In this case, we took from the tracker. So we were able to pull that data and implement it into our F net. And we determine F net is, once again, is equal to Fg plus F contact, and we know Fg is represented by mass times gravity. So simply manipulated that formula and determined force of contact is equal to 8.322 newtons. And from that, we implemented that data into our computational model in V-idle to model our uh, motion of the tennis ball. So here we have the Python coding. So we have ball, mass of the ball, we know as took a simple standard sided ball, 8 grams or 0.058 kilograms. We know the initial position since we dropped it at rest is since we did drop it at rest is equal to vector 0, 0, 0, and the velocity would be 0, 0, 0 as well. The amount is it time of 0. Delta t we set to a small 0.001. G, G hat in that case would be a y. And we determined our d just with trial and error as we have in the past. So we separated a motion into 3 instances: before contact, after contact, and after. So at the time point before while t is less than 0.54, we know that the forces acting on the object would be the weight force and drag. So we simply inputted that and updated that in position and velocity with our momentum principle. And here we have an instance of contact. So we did not include drag, but we did include the contact force. So also with j hat. And lastly, we have the instance where after the ball makes its contact with the ground. So as I was saying, at the time after contact, we know that we once again have the force of drag and the weight force acting on the ball. So we would we have our air score, and at this point we can run model. So as you can see, force of gravity is represented there, and it's hard to tell, but we do have drag force as well. And here is our position over time, which makes sense. As you can see, the ball moves down, and then as it makes contact with the ball, it does bounce back up. So now in comparison, as you can see, the predicted fairly matches the observed. There's a couple of errors in the end, so it's probably a lack of human error due to our traffic data. Overall, you can see the effects. And so from this, we can ask, what does it mean? Why does from the experiment or the lab, we can tell that the ball did not bounce as high the second time as it did. I mean, it did not bounce to its original height. So why is that? As it makes contact with the ground, the ball experiences a release of energy, whether that be thermal or sound energy. So it does lose energy in its reascent. And what if how would position versus time of the graph differ from if there was no loss of energy to surrounding? Well, if there was no loss of energy, then we would have a continuously bouncing ball. So that's my lab 5. Thank you.